Section 4.3 is about connecting the graphs of f prime and f double prime with the original function f. So what can we learn about a function f by examining its first derivative and examining its second derivative? So to start us off, remember what we said a critical point was. It's any place, a critical point of f is any value of x for which f prime is 0 or for which f prime is undefined. And what was the whole reason that we looked for critical points? Because we figured out that relative extreme values, local minimums and local maximums, so tops of hills and bottoms of valleys, occur only at critical points. So just notice here that if we happen to be looking for a relative maximum value of a function, a high point of a function, so like this or like this, we're looking for a place where a function was going uphill and then starts coming back downhill. So this function was increasing. Once it starts decreasing, it's sort of maxed out, it's topped off, and that's where I'm going to find my relative extreme values, so relative maximum values. So we formalize that idea with what we call the first derivative test for local extrema. If a function has a derivative, so a function f has a derivative f prime, and f prime changes from positive to negative at a certain value. It's got to be a critical point. If f prime changes from positive to negative, what does that mean? That means f prime was positive and changed to negative. That means f was increasing, and then f changes to decreasing. What does that give me on my graph of f? It gives me a relative maximum or a local maximum. So if f prime changes sign from positive to negative at some critical point c, then f of x has a relative maximum at x equals c. Similarly, if f prime of x changes from negative to positive, that means f changes from decreasing to increasing, and I get a local minimum. And then just notice this third part here. If there's a critical point c, and f doesn't change sign, so f prime, if there's a critical point and f prime doesn't change sign at that critical point, then there is not a relative minimum or a relative maximum. So that's important because that says just because there's a critical value doesn't mean I have a top of a hill or a bottom of a valley. If I have a hill or a valley, it happens at a critical point, but just having a critical point is not enough. So I'm going to fill in this with a typewriter. So it's called the first derivative test for local extrema because you can tell about the local minimums and local maximums of a function by investigating the first derivative of a function. So to find relative extrema of f, we're going to find out where f prime changes sign. So here's an example. If I want to use the first derivative test to find the relative extrema of y equals x cubed minus 12x minus 5. Well, f has, or in this case y, has relative extreme values where f prime changes sign. So I'm going to find y prime, set it equal to 0. And I'm essentially going to make a number line graph and find out for which values of the inputs, or for which values of x, is y prime positive, negative, or 0. So I've set y prime equal to 0. I solve and I get two solutions, which are positive 2 and negative 2. So I mark them on the number line here. I'm going to test a point from each interval. If I test a point that's a value that's less than 2, I get negative results. If I test a value between negative 2 and positive 2, I get, let me try that one more time. If I test a value less than negative 2, I get positive results. If I test a value between negative 2 and positive 2, I get negative results. If I test a value greater than 2, remember I'm checking in the derivative. I'm plugging these values into f prime of x, y prime. I get y prime values that are positive. So what can I conclude about the relative extreme values? I know that y must have a relative maximum at x equals negative 2 because y prime changes from positive to negative at x equals negative 2. So I see here in my answer, I haven't quite answered the question all the way. I was supposed to find the relative extrema. I have found the location of the relative maximum But now I have to actually find that maximum. So I'm going to do that by taking x equals -2, plugging it in for y, and I'm going to get y equals -2 cubed is -8, minus 12 times -2 plus 24 minus 5. So I would say y has a relative maximum value of, what's that, 11 at x equals -2, because y prime changes from positive to negative at that value. Again, similarly, y is going to have a relative minimum at x equals +2, because at x equals +2, y prime changes from negative to positive. So a relative minimum at x equals 2, to actually find that value, I'm going to have to plug in 2 for x. That's going to be 8 minus 24 minus 5. That's 8 minus 29. Is that -21? So I would say y has a relative maximum of -21 at x equals 2, because y prime changes from positive to negative at x equals 2. This problem is similar. I've been asked to use the first derivative test to find the relative extrema. So I have y is x squared minus 3 times that quantity times e to the x. I'm going to find y prime and set it equal to 0, so I can make a number line graph for y prime. I get two solutions at x equals -3 and x equals 1. Notice that when I factor, here I have 3 factors multiplied together to make 0, which means either x plus 3 equals 0, or x minus 1 equals 0, or e to the x equals 0. Of course, e to the x can't ever equal 0. E to the x is always positive, so that's why I don't have a solution from this factor. It's still a factor in my derivative, though. So now I'm going to come here, I'm going to mark my zeros on the number line. I'm going to test a point from each interval. For values less than -3, y prime is positive. For values between -3 and 1, y prime is negative. And for values greater than 1, y prime is positive. So I'm going to conclude that y has a relative maximum at x equals -3, because y prime changes sign from positive to negative there. And I would also want to be certain that I said that the value of that relative maximum is y equals, I'm going to plug -3 into the original function. Okay, I had to go look up my function. So I would say that y has a relative maximum at x equals -3. To find that value, I'm going to have to plug -3 into the original function. So that's 9 minus 3 is 6 times e to the x, e to the -3. So that value is going to be 6 e to the -3. And I would say y has a relative minimum value at x equals 1, because y prime changes from negative to positive there. And that value, to get it, I'm going to have to plug my x value into the original function. So this one was -2 e to the first, or just e.